Hello again, welcome to another lesson in Algebra 1. Today we are covering the guided notes on Module 1, Lesson 8. Okay, so how many quarters, nickels, and pennies are needed to make $1.13? That was our warm-up question. All right, so we want to use the biggest amounts first, so we're going to get as many quarters as will fit. So we're going to get 4 quarters in there. Okay, that will give us $1. So 4 quarters is equal to $1. Okay, and now we still need 13 cents, so we might as well go with nickel because we're not allowed any dimes here. So nickels will give us, let's see, 2 nickels. So this will give us 10 cents. Okay, and then lastly, we're going to need 3 pennies. And together that'll make 113. Okay. All right, then you're asked to fill in the blanks here for some numbers, so we're breaking it down. So 8,943 is the same as 8 times 1,000, 9 times 100, 4 times 10, and 3 times 1. Okay. Now remember, look at these. These are powers of 10. 1, 10, 100, 10, 1,000. So that 1 is 10 to the 0 power, so this is still going to be 3 here. 10 is 10 to the first power. So 4 times 10. 10 squared is 100, so this is still going to be 9 times 10 squared. And 10 cubed is 1,000, so this is going to be 8 times 1,000. So we're just writing their numbers using base 10 instead of 1, 10, 100, 1,000. Okay? All right, so fill in the blanks here. We want to do base 20. All right, so I don't have base 20 memorized, so we need to figure out how many 20 to the 30th power? How big is that? So 20 to the 30th power is 20 times 20 times 20. So that's 2 times 2 times 2, which is 8, and then 3 zeros. So that's 8,000. So we need 8,000. Clearly there's not enough, another 8,000 inside of that number. Okay, so far we've collected 8,000. Now 20 squared, 20 times 20 is 400. We have 943 left to cover. So we're going to take 2 of those, okay, which will give us 800 extra. All right, so far we're up to 8,800. All right, so then we're going to pick as many 20s as we can make fit. Well, what do we have left? We have 143. So 143, that's going to be 7 20s. Okay, so that will give me 140. And then I still need 3 more. So 20 to the 0 power is 1. So I need 3 of those. All right. So this is 1 times 8,000 is what this really is. Plus 2 times 400. Plus 7 times 20. Plus 3 times 1. Okay. All right. Fill in the blanks. 113, we're going to change that to a number in base 5. So how many 5 squareds will fit into 113? Well, 5 squared is 25, so that means I could use 4 of those to get to 100. Okay, still have 13 left though. So how many 5s will it take? Well, that's going to be 2 of those. So 5, and we'll have to times that by 2 to get us 10. And then we need 3 1s. Now this one should look familiar to you. If you go back up here, that's our 4 quarters, that's 4 times 25, plus 2 nickels, that's 2 times 5, and 3 pennies, that's 3 times 1. Okay, these are, once again, 5 squared, 5 to the first, and 5 to the 0. Okay. All right, so money, with the exception of our dime here, so far we've seen as base 5. All right, base number systems. So the penny, the nickel, and the quarter are all base 5. So base number systems in mathematics, a base or a radix is the number of different digits or combination of digits and letters that a system of counting uses to represent numbers. Why do modern humans count using a base 10 number system? So this was us just brainstorming in class. So why was exercise 2 an example of using the base 10 number system? Base 10 number system, we'll go back and look at that in a minute. But if you think about this one, This one's pretty common. Why we count with base 10? How many fingers do we have? Okay, so we have 10 fingers. So we count in base 10. Now, a computer counts in base 2. Okay, and the reason for this is a computer has circuits, and each circuit can be turned on or off. That's two things they have to count with. On for 0, off for 1, or the opposite. Okay, so we have 10 things to use to count with quickly, looking at all of our fingers, so that's why we use base 10. Why was exercise 2 an example of a base 10 number system? So let's go back up and look. And you can see in exercise 2, we were using all powers of 10 to help represent the number. Power of 10 here, this is 10 to the 0, 10 to the 1, 10 to the 2, 10 to the 3. Okay, so we used powers of 10 to represent the number. And we are so used to using powers of 10 that when we see a number like 8,943, we automatically think 8 times 10 to the third power, 9 times 10 squared, 4 times 10 to the 1, okay? Which doesn't have to be the case. If we were writing 8,943 using base 20, our number would actually be 1273, okay? And somebody who lived on a world that had 20 fingers might think that that's how you represent 8,943 things. Okay. All right, so when writing numbers in base 10, we allow coefficients from 0 through 9. Okay, so that's the number that comes in front of the base 10. Why is that? Well, once again, this is 10 things. Okay, so it makes it easy to see which of those 10 things we're using. So if you were representing a base 2, your numbers would go from 0 to 1 for the coefficients. That's 2 things. And we need a 0 here now, so we don't go from 1 to 10 for the coefficients, because we need a 0 to show an absence of that number for that base. So 0 times 1, or 0 times 10. Okay. So what base number system do computers use? And we've been talking about that for a while. Computers use base 2. And the why is circuits can be on or off. So circuits have 2 states only, which are on or off. So in other words, they have power or they don't have power. All right, let's flip it over. Now let's be as general as possible by not identifying which base we are in. Just call the base x. So consider this expression. 1x cubed plus 2x squared plus 7x plus 3 times 1. Or equivalently, x cubed plus 2x squared plus 7x plus 3. So this is just a polynomial. What is the value of this expression if x is 10? So they're saying, okay, let's evaluate the polynomial if this was really base 10, not base unknown. So x is our unknown base. And we're going to go ahead and evaluate this for base 10. So this would be 10 cubed times 1, right? Plus 2 times 10 squared, plus 7 times 10, plus 3 times 10 to the 0. So it goes 0, 1, 2, 3 for our exponents. So 3 times 10 to the 0, that's just 3. So that's easy. 7 times 10 to the first, that's 70. So that puts a 7 in the 10 spot. 2 times 10 squared, that's 200. So that puts a 2 in the 100 spot. And 1 times 10 cubed is 1,000, so that puts a 1 in the 1,000 spot. So what is the value of the expression if x is 20? So if this was a base 20 number, we want to go ahead and figure out what the value would be for us. So let's see. So that would be 1 times 20 cubed plus 2 times 20 squared plus 7 times 20 to the first power plus 3 times 20 to the 0 power. Now, our final answer for this is going to be in base 10 because we're going to make this a base 10 number in the end, but we're working this out as if the unknown base was 20, and now we're going to convert it to base 10. So 20 to the third power, one more time, was 8,000. So that's 1 times 8,000. Okay, so I'm going to write 8,000 under here a little, times 1. 20 squared is 400, so this is 2 times 400. 20 to the first power is just 20, and 20 to the 0 power is 1. So what we're doing is 8,000 plus 800 plus 140 plus 3. And this would be 8,943. Okay. So what is the value of 22x plus 3 when x is 5? So this is asking, looking at base 5 for this polynomial. So our unknown base, x, is going to turn into base 5. So this is 22 times 5 plus 3. So this would be 22 times 5 is, and then we add on 3. So 22 times 5 is 110, plus 3 would give us 113. And then our next question was, how much money is 22 nickels and 3 pennies? Now we don't have to do any more work for this. That's what this expression says when I put 5 in. It says 22 times 5 to the 1 power plus 3 times 5 to the 0 power, which is 22 nickels. 5 to the first power is worth 5 cents a piece. And 5 to the 0 power is 1 penny a piece, 3 pennies. So this is exactly the same thing, 22 nickels plus 3 pennies. So we know my value is going to be 113 cents. Okay. What number is represented by 4x squared plus 17x plus 2 if x is 10? So it's saying take our unknown base and put a 10 in there for the base. So this is going to be 4 times 10 squared plus 17 times 10 to the first power plus 2 times 10 to the 0 power. And we don't need to write 10 to the 0 power or put a power of 1 on the 10. So this is 4 times 100, which is 400. 17 times 10, which is 170, plus 2. And then we can put those together to get our base 10 number, which is 572. So what number is represented by this polynomial expression if we're going to do base the square root of 2? All right, so that's a little trickier. So negative 3 times the square root of 2 squared plus the square root of 2 times the square root of 2 plus a 1/2. All right, so the square root of 2 squared. Well, the square root and the square cancel each other out, so they just make 1. So this becomes negative 3. Plus the square root of 2 times square root of 2, that's just 2. Let's see. And back here, square root of 2 and square root of, and the square root and the square cancel each other out. That was supposed to be negative 3 times 2, which was negative 6. Okay, so this turns into 2, and 2 times negative 3 is 6. These two together turn into 2. Okay, and then we have plus a 1/2. So negative 6 plus 2 plus 1/2. That's negative 4 plus a half, which is negative 3.5. All right. So a polynomial expression is either a numerical expression or a variable symbol, or the result of placing two previously generated polynomial expressions into the blanks of the addition operator or the multiplication operator. Okay. So that seems all weird looking, but just think about this. Polynomial expression could be a variable symbol or a number. Okay, a numerical expression. Okay, and then to make it be other polynomials besides just a variable or a number, we can multiply these together. So we could do 2 times x. We could add these together, and then we could take these new ones and combine them again also. Okay, so we can put them together to get polynomials. As long as we start with polynomials, we can add 2 to get more polynomials, or we can multiply 2 of them to get new polynomials also. So for each sum or difference by combining the parts that are alike. So 417 plus 231. All right, well, let's put them together first. So that's 4 100ths, 110, and 7 ones. And then 2 100ths, 3 10s, and 1 1. Okay, so we are going to do our hundredths. How many hundredths do we have? Well, we have 4 hundredths here and 2 hundredths here for a total of 6 100ths. And how many tens do we have? We have 1 10 here and 3 10s here for a total of 4 10s. And then for ones, we have a 7 and a 1 for 8 ones. So that's 6 100ths, 4 10s, and 8 ones. So this makes 648. Okay. And then for part B, we're going to do the same thing by combining our like terms. So the 4x squared can combine with the 2x squared first. So we'll do associative property to drop the parentheses because they don't matter here. And then we're going to rearrange them and put the parentheses around the 2x squared and the 4x squared. And then we'll also put some parentheses around the 3x and the x. And we'll also put some parentheses around the 7 and the 1. So this will become 6x squared plus 4x plus 8. All right, that completes our second page. Let's look it over, do some more combining of polynomials. In the previous example, we added 2 polynomials. This time we're going to subtract 2 polynomials. And remember, a polynomial is just a base number that we don't know the base for. So before I do that, let me just subtract 2 numbers. If we're subtracting 523 minus 211, okay, we don't just do 5 minus 2 for 3 and then add the other ones on, right? We don't say 3 and 4, so 334. We subtract each part of it. Remember, we do 5 minus 2, and then we also do 2 minus the 1s, and then we do the 3 minus the 1s. So we subtract each of its corresponding base part. Okay, so we're going to do the same thing here. So when I'm subtracting 2 polynomials, okay, then I need to do 3x cubed minus x squared plus 8 minus each one of these parts of this polynomial. So minus x cubed, minus 5x squared, minus 4x, and then minus a negative 7. Well, minus a negative 7 is just add 7. So don't write it with 2 signs. Okay. And now we'll combine the like parts. So we can put our x cubes together. Okay. So the parts that go together for the cubed part of our unknown base. So 3 minus 1 is 2x cubed. And then we can put our x squareds together. We have negative x squared and negative 5x squared. So negative 1 minus 5 is negative 6x squared. And then we can combine our x, but there's only one of them. Okay. And then we put our last bit, which is positive 8 with positive 7. So that'll make positive 15. Now just be careful with the sign here. So it's subtract all of the pieces of the second polynomial. So it's kind of like distributing a negative. All right. Okay, part D, we're going to put a little distributive property inside of this problem first. So we have the product of 2 polynomials, and then we'll combine up all of our like terms. So 3 times x cubed will give us 3x cubed. 3 times 8x will give us 24x. So I distribute the 3 for the first part. In the second part, I'm going to distribute the subtract 2. So negative 2 times x cubed will give us negative 2x cubed. And negative 2 times 12 will give us negative 24. And then we'll go through and combine our like terms. So once again, we have some x cubes. Those guys will go together to make 1x cubed. 3 minus 2 is 1. And then we have some x's. And then we have minus 24 by himself. So 24x and minus 24 had nobodies. All right. Now for part E, we're back to some adding. So adding 2 polynomials. So 5 minus t squared plus 9t plus t squared. And combine up our like terms. So we have negative t squared and positive t squared. Those go away. So nothing to write there. Then we have 9t and minus t. This will make 8t. And then lastly, we have a 5 by itself. So plus 5. All right. In part F, we're going to add and subtract some polynomials, but we have to complete this distributive property first. So the first polynomial doesn't have anything to be multiplied by. The second one has a positive 6 to be multiplied by, so that makes plus 6p, and 6 times negative 8 would be negative 48, so minus 48. And then our third polynomial is a subtraction, so we need to subtract each part. So subtract p and then subtract a positive 2, that's just subtract 2. Okay? We'll combine up all of our p's together. So there's 3p plus 6p and minus p. So 3 plus 6 is 9, minus 1 is 8p. And then we have 1 minus 48 minus 2, so that's negative 50 plus 1, which is negative 49. Okay, so a couple more definitions here. Okay, so we have a monomial. So a monomial is a polynomial expression generated using only the multiplication operator. So there's no addings and subtractings in it, it's just all multiply. Okay. Thus, it does not contain add or subtract operators, and monomials are written with numerical factors multiplied together and variable or other symbols, each occurring only one time. Okay, so we can't have like 2xx. So instead, we would do 2x squared. Okay, that's okay. So we only use the x one time and put up exponent on it. Okay, we also don't put 2x squared times 4. We just make it 8x squared. All right. So a polynomial is just a sum or a difference, so add or subtract, a whole bunch of monomials together. Okay, and this is how we created polynomials before, remember? We use the multiplication operator to make something, or the add operator to put two of them together. So degree of a monomial is the sum of the exponents of the variable symbols that appear on the monomial. So this small monomial here, this has a degree 2. It has only one exponent on its variable. Okay. The degree of a polynomial is the degree of the monomial term with the highest degree. So we do each of them separately and find the highest one. Okay. And then the leading coefficient for a polynomial is the coefficient of the first term when the polynomial is written in standard form. And we'll talk a little more about what that means in a second. Okay. All right, so number 9, we want to find the degree of each of these monomials. So read the definition of monomial above and circle any polynomial below that is not a monomial. Ooh, so we're not finding the degrees, we're just circling the ones that are not monomial. So monomial is created from a number and variables multiplied together. So this one's okay, that's 2 times x. 2 is fine, that's created from a number. 2x squared is fine. Oh, I'm circling the ones that are not polynomials. Okay, not monomials, so I don't want to circle those. Those are good. 2x is good, 2 is good, 2x squared is good. This one's fine. We have x and y only occurring once. The y gets a square to show that there's 2 of them in there. Negative 3 in front. This one's the bad one. This plus in here makes me have to circle it. Remember, a monomial does not have add or subtract in it. And this one's fine. Okay. All right, number 10. There are polynomials called binomials and trinomials. Can anyone tell us an example of each? So in class, a binomial we found out was 2 monomials added together, and they cannot be like term monomials, otherwise we can just create one single monomial from them. So binomial is 2 monomials added up, and a trinomial is created from 3 monomials added together. All right. And then we have, write the degree of each polynomial in the expression below. So here we're looking for degree this time. So this is 4x. So what's the sum of the exponents on the variables? Well, this exponent has a variable, or this variable has an exponent of 1. So that's the only one there is, so this would be 1. Okay, for part B, we have 2 variables and they both have an exponent of 1. So the sum of their exponents is 2. For part C, we have 1 variable and its exponent is a 2. So the sum of the exponents is 2. And part D, we have 2 variables, x and y, and the sum of their exponents are 1 plus 4, which is 5. And part E, this is a binomial, so we have to look at each monomial separately. So this part has a degree 1, this part has a degree 1, the largest is 1. Same thing with part F. This monomial has a degree 3, this monomial has a degree 1, so the largest of those is 3. Okay. And for part G, this monomial has a degree 3. This one has a degree 2. This one has a degree 0. Okay, it has no variables, so all the variables would have exponent of 0 to make them turn into 1. And the largest is 3. And in our last one, this is degree 4, this is degree 1, so the largest is 4. So when it's a monomial, you just add up all of the exponents on the variable terms. When it's a polynomial that is not a monomial, so it has 2 or 3 or 4 terms, you each term separately, each monomial part separately, and then find the biggest one. All right, so rewrite each polynomial in standard form if needed and say what the leading coefficient is. So here's how we do standard form. We put the terms in order of their degree. And then if two terms tie for the highest degree, then we put them in alphabetical order. Okay, so this one is 5x. He's already got only one term. And its degree, the leading coefficient here is the number in front. So 5. So this was degree 1 with the leading coefficient of 5. Our second one, here's degree 2 and here's degree 1. So it's already in order. So 2x squared plus 5x. And when it's in order, we look for the number in the front, the coefficient in the front, and the leading coefficient is 2. Okay. This one has degree 3, this one has degree 4, so this is not correctly ordered. So we have to reorder this polynomial, 2x to the 4th power plus 3x cubed. And now the leading coefficient is a coefficient in the front, and in this case, once again, it is a 2. All right, so this is degree 1, degree 2, degree 0. So we have to reorder it with the negative 2x squared in the front, and then the positive 3x, and then the positive 5. So the leading coefficient is negative 2. And lastly, we have x squared plus 2x plus 3 when I reorder it, because that's degree 2, degree 1, degree 0. And the leading coefficient is the number in front here, and since there's no number in front there, it's a 1. 1x squared is what we have. All right, so you were supposed to complete Lesson 8 problem set exercises 1, 2, and 4. And then there's some extra problems, E1 through E3, that you need to do. Please make sure you're doing it on your recording paper, and I'll see you in class next